Okay, let's start today's session. Uh, I hope you had a great day today. In today's discussion, we are going to talk about the introduction chapter one, and we are going to talk about some concepts, some very general kind of like definitions that we are going to have. So basically, creating the ground for our discussion through the semester. Now, uh, we are going to talk about one of the most powerful and fascinating, basically, and practical systems and concept in electrical engineering, which is the control system. And we are is not just about knowing how the equation works and how we could solve the equation, our discussion through the semester, or how we can draw the block diagram, or how we can just develop the transfer function. We are going to talk about those concepts in a way that we could understand basically how those machine or system works, how we can design the processes, and how each of our system would respond to a certain transient uh, behavior and input, and what is the error of our system from the desired state that we want to have at the output. Okay? Now, today we are going to talk about actually what are the control system are, why they matter, and how we can classify them in a general category, and basically start the discussion of how to analyze and design the control system. Now, when we talk about the control system, the definition is we have a system, including some subsystems, okay, that run through a certain processes, okay, to obtain the desired output, okay, a desired performance, and making sure we have a stability in a certain specific input and under a certain specific environmental condition. Okay, so this is what we are gonna have as a definition of a control system. So what are the aspects? Again, we have subsystems in our control system. We have processes that we need to assemble and analyze. The goal that we have is to get the desired output, regardless of what is the situation of the input, okay, or what is the situation of the environment. Now, when we talk about the response to the input, we normally have two types of response. One would be the transient response, okay, which we also could call it a natural response, okay. Another one is a steady state error. Now, what are these? When we talk about the transient response, we are going to talk about how the system would react to a change in the input, or a change in the conditions of a system, or a change in an environmental condition. Okay, so whatever cause that we have to have a fast change in our system, then our control system would have a transient response to that change. Okay, now what is the steady state error? After our transient or our changes kind of settle down, we are going to have a steady state condition when the system settles down to a certain state. Okay, now we could have multiple states during the time, so system could kind of like transfer from the state number one to state number two. But when we settle down, we have a steady state condition. None of the system that you are going to design in actual world would exactly give you the output that you desire. We are going to have a certain error in our steady state output from the desired value that we designed the circuit for. Okay, so that difference between the actual output and the goal, the desired value that we have, we call it a steady state error. Okay, now remember, transient and a steady state error are in two different states. They have two different physical characteristics. Okay, try to search on a transient state and a steady state to kind of like have a good understanding of what actually they mean. Okay, now why actually these control system matters? What we can get out of a control system? There are several aspects that we could have out of a control system. One, this is the advantages. One is a precision. What that means, we don't want to just reach a target. Okay, we want to stay on that target under any transient condition. So precision is one of the advantages of a good control system. Another advantage is automation. Okay, that means you have like a certain level of intelligence in your control system that if you wanted to like have a persistent process without always having a human supervision, okay, which is the definition of automation, basically. Now you need the control system. This is one of the advantages of the control system, because we are going to talk about a certain specific category of the control system has the ability of self-adjusting. Okay, so you don't need to actually manually adjust and eliminate the errors. The system would do that for you. It is very obvious, like when you have like an industrial manufacturing plant that works 24/7, automation would reduce the cost significantly. Okay. Now, another advantage is the regulation. Okay. What that means, we have certain parameters, certain variables that we want to hold on to. Now, holding those variables like voltage or speed or temperature at a desired level, it's what we call the regulation that we can have that from a control system. So regulation means it would regulate our system and keep the desired value at our output with a certain error. Okay, we can't eliminate the error. We can attenuate it. We can't eliminate it. Now, another thing is a compensation. It's in the name. As we said, we always going to have changes in our conditions or our input. Okay, and there are going to be a certain drift or error that could happen. So all the error are not like a bias, like an offset, a constant error. Like it's not like your system is going to be like, for example, if you have like a 1 volt error in your output of the circuit, is not like through the time it would stay at 1 volt. Okay, we also could face some drift, which is the error changing and accumulating through the time. Okay, so this compensation, that advantage, not only help you to kind of like deal a little bit with that DC or a constant offset error, but also help you to compensate from all the deviation that you have in your output from your desired value. Make sense? So these are the advantages of the control system that we could have. Now, when we talk about designing control system, we have a certain objective, or analyzing, both of them. okay, analyzing and designing, we have a certain objective. So it's not like just we haphazardly, solve some equations and see what's going to happen. It's not a math, exam every time you analyze a control system. You have a certain objective. What are those objectives? What are those goals? One is the transient response. So you want to see what would be the behavior of your system in a transient response. Another one is a steady-state response. So when the conditions settle down to a certain state, now what would be the behavior of your system? It is not always like a purely electrical system or purely mechanical system. We might have some like, energy conversion between the two field of, physics, or like we can have like all like electrical values, mechanical values, like temperatures, or like chemical kind of like description in one system. Okay, each of them could introduce a transient into our system, which our objective is to analyze the transient response and see how it would work and how it would react. But at a certain amount of time, when a certain amount of time passes, okay, we are going to settle down eventually in a certain state. And we have to know, okay, when we settle down and we are in a steady state, now what's going to happen in our system? This is the steady state response analysis. Okay? Now, one of the very important and critical aspects of control system analysis and system analysis is the stability. Okay, yes, you have a very good design. It could handle the transient properly. It would gives you a very kind of like a minimalistic error, okay, in a minimum error possible in your steady state. You compensate the drift, all of them, okay? But if you have a system that have a vulnerability, especially like regarding the stability, then in a certain condition, your system could fall apart. And we would have like a very kind of like critical situation in our system. So it would not react as you intended. We are going to talk about the stability analysis and what we mean when we say in a certain condition. Okay, now I'm going to open a parenthesis. When we talk about the physical system, it's all about frequency and vibration. Okay, whatever we have is frequency and vibration. That's why we always deal with the sinusoidal kind of a function or exponential function. Okay, so when we talk about the steady state, or if you have like an eigenvalue, if the concept of eigenvalue, we are going to talk about that in detail later. Okay, all of those basically eventually refer to a certain stable vibration. Okay, that's what we call it a state. One example, like for the water, we have three states. It could be a solid, ice. It could be a vapor, gas state. It could be like water, liquid state. We call those three states. Now, the definition I told you is that all about the vibration and frequency. What is the difference between the two states? It's the frequency of the vibration of the molecules, okay, in that specific material. If you have a very low frequency, you have a solid, you have ice. If you have a relatively higher frequency, you have a liquid. If you have a very high frequency, it's going to be vaporized. That's the energy. You give, like you heat up the water, you give the energy that makes more vibration. Okay, it's a very lousy kind of like very general description, but eventually it's come to that part. Now, when we talk about the stability, okay, you're going to see that in a certain state of a system, meaning we have a certain frequency. Okay, it's not like we only have one state in our system or one frequency in our system at a time. We could have a combination of several kind of like frequency and vibration in our system. Okay, it could be an input or the reaction of the system to the certain input. Okay, it doesn't matter. But some of those vibration could critically deviate the behavior of a system, which means we don't have any stability. One example would be the effect of the resonance in our system. Okay, if we have a certain frequency in our system and we enter the resonancy, then the system would not behave as we intended, and it literally could fall apart. Okay, now there are other consideration. Okay, like hardware selection is not like we have everything that we need in outside world. Like for example, you design a circuit, you say, okay, I want to need like this amount of resistance or that amount of capacitance in my circuit. Okay, that's not going to be out there. You have to calibrate. Okay, so you have a hardware constraint when you want to like deal and design with your system. Another aspect is the cost. We're an engineer. Okay, first priority is money. Okay, then we try to help society and advance the scientific aspect. Okay, so cost-effective situation is very important when you design a system. Okay, now that's why you don't have quantum computer at your home. Okay, so it's the mind. Robustness is another aspect that we need to have and we need to consider when we're analyzing our system. Now, let's talk about like a short history of where that control system begins. Believe it or not, control system is one of the ancient kind of like a part of the science and technology that exists in the whole human history, the whole civilization. Okay, an example of that would be like the float valves that they would use like in 2000 3000 BC in like a grid to control the level of the water in a certain container or tank. Okay, that is a control system. Very simple, but this is the control system. Okay, or when we have like an industrial revolution, okay, we were introduced to the steam engines. So they normally work with a centrifugal governor, which was a weight that rotates and basically controls the speed of our system by controlling the amount of steam entering the engine. Okay, so that's also a control system. Now, when we talk about a dramatic kind of like evolved method technology, like now in a 21st century, and basically after the 20th century, we had a lot of breakthroughs when it comes to the control system and analysis of the systems within the field of the control theory. We will get introduced to the Laplace transform. Okay, it was developed in 20th century. We have the frequency response. Someone invented and developed the frequency response method, so we can easily kind of analyze the system. We developed PID controller, okay, or one of the very sophisticated yet simple, okay, method, which was the status space theory, okay, which helped us, all of them helped us to have an easier kind of like situation when we want to like analyze or design the control system or any type of system that we design or like we have. Now, today, the control system is everywhere. In your phone, in your car, there are drones that you work with the control system or satellites and even like biotech devices. They all use control system to help them to maintain a certain output or deal with a certain disturbance. Now, we said we wanted to like generally categorize the control system, and the category that we have, like this is a very kind of like fundamental level of categories. Okay, each of them has their own specific subcategories that we are going to talk about later. Okay, now the two fundamental categories that we have for a control system is two categories: open loop control system and closed loop control system. Now, what are those? When we talk about the open loop control system, the definition is the control system that only relies on the input to basically control the system and adjust the values. Okay, so this one cannot compensate the errors because there is no observation on the output. Okay, all it sees is the input. If input change, it would change the behavior. It cannot compensate the environmental change. Okay, it cannot deal with a drift. So it's very cheap technology, inexpensive technology, very easy to implement, but the downside is that you lose a certain advantages that you want to get from a control system. One would be like your a microwave oven, okay, in your home. You set like 30 seconds for the duration of working for that microwave oven. Okay, the microwave oven doesn't care how much your food inside the oven is heated, okay, or how much energy or like what is the situation actually inside the oven. It just provides you 30 seconds of performance. Okay, so there is no observation of what's going to happen at the output of that performance. The input is 30 seconds, it would work for 30 seconds. Same for your like gas oven. It is the same. It doesn't care. Like you set that gas oven in high. If there is an error in the valves, which makes that like you set it at a high level, but is not gonna actually get to the high level. So system would not understand that. You know what I'm saying? So if there is an error, it cannot understand it, therefore it cannot compensate. Okay, now you can see in the graph, if we have any disturbance, it would not affect the control system because controller is before those. Okay, it just affects the output. Now, another category is the closed loop control system. Now, in the closed loop control system, we have a certain aspect named feedback. So it's not like the system would work blindly. It actually observes what is the result. Okay, so for example, your air conditioning, okay, you set that as a temperature, at a temperature. Okay, it's not just cooling down or heating up. It actually measures the temperature and tries to eliminate the error between the actual temperature and the desired temperature. So there's a feedback. Okay, so it has a certain intelligence in it. It would observe the error. It would calculate the error. It would observe the disturbances. And if we have any factors that could affect the performance of the system for a specific output to get a desired, for a specific input to get the desired output, now that closed loop could compensate all those deviation and disturbances, all those error. Okay. Now, they have, you can say there's error correction. In a feedback, we could have noise reduction. Okay. We could have like a better accuracy when it comes to the performance and stability, actually, performance of the system. But what is the cost that we have to pay? It is more complex. It is more kind of like relative to the open loop is more complex. Okay, and since we have a feedback, now we are gonna have a serious problems when it comes to the stability of the system. Okay, so if the feedback would not work properly, you can imagine it would, instead of eliminating the error, it would add to the error. Okay, so, or in a certain kind of like frequency, it would actually transient, and instead of basically eliminating error, is just alternate around that value. Okay, I did mute my computer, did I? Yeah, okay. Now, we talked about the two general category of the control system. Okay. Now let's talk about what are the steps, the general steps, when we want to like design or analyze a control system. When I say design, I put design process because analyze is a part of designing. Okay, we are going to focus on that, but it's part of the design. Now, the first step is to actually look at what we have, the physical system, okay, and determine what is the specification of that system and what are the requirements that we. For example, we wanted to like control like a voltage or a temperature or a speed, and the requirement is that we have to have a certain threshold for the error. This is like a very simple specification and requirement. Another specification would be like, okay, if we wanted to like control the voltage, but the range of the voltage, the nominal voltage that we have is in a certain margin. These are all a specification and requirement that we need to follow. Okay. Now, when we defined the system specification and the requirement that we need, now we should have a general architecture of our control system. Okay, we call it block diagram. So we need to develop the block diagram. What that means, like you can see that in the previous slide. There is no actual schematic in this block diagram. Okay, it just says, okay, I have an input, then I have a transducer to pre-process that input. Okay, this comes to that requirement. Like you have a certain requirement for the input or certain specification for your physical system that makes you force you to need a transducer, for example. And then you have a controller. After that, you have a process. That process could be like a low-pass filter or any type of process. Okay, you could have a feedback or you don't like an open loop system. If you have a feedback, that means you have observation, which means you have a sensor, and you have to deal with the output of that sensor. Okay, this is the general idea. So, and at the end, you have your output. General architecture. We didn't talk about the specific design or what's going to happen in each of the blocks. Okay, so this is the step 2. The step 3 is transfer those blocks and those physical kind of like architecture to a schematic. you wanted to like have a controller, for example, you want to have like in a specification, you decide to like have a PID controller or PD, we are going to talk about that, or a PI controller. What is the schematic for that? Okay, and a schematic, I don't mean just like electrical schematic, it could be mechanical schematic too. Okay, is a design. What type of component you need to get what you want out of that block. Okay, then in the third step, we talk about in the fourth step, we go from that schematic. Now we have our schematic. We go from that schematic to mathematical analysis. So now we have the component. We know how they behave to a specific input. So we can understand the equation, the mathematical equation that describes how that system would govern. Is that make sense? Okay, so the equation that governs the system comes in a step 4. You have your system schematic. You develop the ODE or kind of like a frequency domain kind of like equation that describes the behavior of that system. For example, you have like a, let's say, a RC circuit. You run a KVL KCL on that circuit, and you find out, okay, what is the relation between the output and input. The equation that describes that is the equation, the mathematical equation that governs the system. Has 2 parts, transient and a steady state. Okay, now, if we have multiple blocks, when it comes to have like a stability analysis or a frequency response analysis, okay, or even like sometimes like when you want to deal with the time response, okay, when you have a very complex or multiple blocks in your system, that means you have multiple schematic in your system, it's going to be hard to only use those very detailed equation and run the analysis over the whole system. So we try to simplify our block diagram, combine them, some of the parts. Like for example, in this block, okay, we can easily see that if, for example, you can consider like, it's not true, but you can consider this block as a certain coefficients, as an amplifier, a simple linear amplifier. So it's a one scalar gain. So instead of like the input VI, you can eliminate that and say it's like alpha VI. Makes sense? So you will eliminate that one. You have a feedback. We are going to learn what it means. So we have output. What is the output here? Like for example, we have that alpha VI minus whatever happening here times V out goes to the controller, get times multiplied by a certain equation or a behavior, get the disturbance get added, again goes through a certain multiplication of the transfer function or equation here, another disturbance is gonna happen, and then we have V out. Okay, so we have a left side of equation, and right side of equation. Now, like for example, you can see in a closed loop, we have a certain value comes from the output. So this is an equation. You know that, okay, now you have to transfer that over there, and we have a mathematical kind of like derivation to find out what is gonna be the equation that generally describes output versus input. Now, that function that we develop by going through everything, okay, could represent one block, could be inserted in one block, meaning we simplified all these chaos into one simple transfer function or equation, or the equation. Makes sense? So this is simplification that could help us have an easier analysis process. Now, when we had the function that describes the relation between output and input in our system, now we can analyze the system, okay? Decide what type of values we need to get a certain behavior out of our system, what type of values we need to stay away so we don't mess up with the stability, okay? Or, for example, or generally, what is going to be the behavior of our system? Okay, if we have a certain amount of input, what's going to happen at the output? If we have a transient, what's going to happen at output? Okay, now this is where we are going to talk about that. This part is where the Routh-Lucas method would comes in, or the frequency response would be evaluated. We have time domain methods, we have frequency domain methods, we have mode plot, we have like a Nyquist. Okay, all of them would happen in that step 6 when we want to analyze our system. Now, we said in current level of technology, we have some very complex system that if you want to run the analysis manually by hand, you probably gonna for example, analyze one system, and after you get the result, you are retired. You know, it's gonna get a lot of time from you to analyze and set the adjustment. So it basically out of the picture. You don't do that. You don't do that. It's not engineeringly efficient. Okay. Now, what we can do is we have some tools that could help us. Computer-aided designs. We call it CAD for short. The most popular one and the most helpful one are MATLAB, which could be including the coding and the simulate, okay, and the LabVIEW. They could help you, you can simply add the specification of the system, okay, and ask MATLAB to, develop the steady state with one line code. Develop the steady state function, one line code, instead of going through the whole of KVL, a hell of an analysis by hand. It gives you the linear algebra model, the matrices that you want. Okay, or you just create the system in Simulink, put the components over there, okay, and run a mode plot analysis. It gives you the mode plot. It gives you the Nyquist. So it helps you a lot to work with that. And like another example that we said it's not like we only have like electrical system or mechanical system. Sometimes they are mixed. Okay, and you have a mixed system. Now Simulink could help you a lot because you can mix several aspects, like several type of system in Simulink. Make sense? Now, sometimes you have some certain control system, like a digital control system. Okay, and you want to simplify it or get the transfer function of that system. Okay, then LabVIEW comes in. You design that, you run the analysis in the LabVIEW, and it gives you the transfer function. It gives you the behavior of the system, and it simplifies that. Okay, so we are going to work with that, with those two tools, MATLAB, specifically MATLAB and LabVIEW. Okay, so we'll learn how they can help us and how we can work with those tools within those software when we want to like analyze or design a control system. Okay, any questions so far? No? Okay. Let's wrap up our discussion about the big picture of the control system. Now, we said the control system analysis and design focuses on three main objectives. We want to produce a desired transient behavior, transient response, okay, which means we have to run transient analysis, okay. We need to reduce the steady state error because, again, we want a desired output for each specific input, okay. So we need to run steady state analysis, okay. And it's not just the behavior of the system or the performance of the system. Our system should be reliable, meaning we should have a stability. So now we need to run some analysis on our system so we know if the system are stable or not, or if there is any kind of like situation, any type of condition, any type of a state, or at any type of any value of the frequency that could jeopardize, okay, the stability of our system. And can we deal with that? Can we kind of like solve the issue by adjusting or like modifying the system or not? Okay, now we also said we have some steps for design and basically analyze the control system. We first start with the determination of the physical specification and the requirement of the system. Then we are going to develop the general architecture calling block diagram of our system. We are going to turn that block diagram into a schematic. Okay, so we know what's going on in the system, what component we have in the system. So if we wanted to like develop the ODE or transfer function of each individual block to see what's going to be effect of that specific block on our input, so we get a specific output. Okay, now it's on the step 3. So we develop the schematic. In a step 4, we mathematically model that schematic, which basically is the ground of our analysis. Okay, we try to reduce and simplify that model, that block diagram, so we don't go through the hell of a kind of like analysis and mathematical derivation. And at the end, we start an analysis. Now we have a simplified version of the equation, either ODE or the differential equation or the transfer function in a frequency domain. Okay, and now that we have that, we can see, okay, for any specific input, like for example, if we have like a delta Dirac input in our system or a step kind of like a signal in our system, okay, or a sinusoidal signal in our as an input, what's going to happen into our system and what's going to be the output of it. Okay, so this is basically the analysis means. Now, it's not just about the performance, as we said. It's one of the most important part is the stability. So it's also about the stability of the system too. Okay, now it includes transient response and steady state response. Please, this is important. Okay, so because I see sometimes like in electrical design, you focus only on a performance, meaning only on a steady state. And when you deal with a transient, if any disturbance happens, then your system is going to be acting like crazy, kind of like lunatic. Okay, so pay attention to both part of the transient and steady state analysis. So this is it for today. we wanted to like just describe the general view. We have a general understanding of what we mean by control system, what are the objective of the control system, and what we are gonna learn through the semester about how to design and analyze the system. Okay, and from the next session, we are gonna start going through the actually how to analyze a system. We are gonna start with frequency analysis, frequency domain analysis, and move on to the time domain and time response and see how we can analyze the system and what's going to be the behavior of the system regarding each specific input. Any question? No? Okay, thank you very much. Have